Good morning, ladies and gentlemen. Happy Wednesday. Today is April 15th, 2020. Welcome to another episode of Mr. Vasquez's Math Lessons. For today, we're going to be taking a look at Lesson 4, Quadrilaterals in Circles. That's right, we're not putting triangles in circles this time. We're putting quadrilaterals. Let's take a look, shall we? 4.1, Connecting the Dots. In this activity, we're supposed to use our compasses to draw circles around these quadrilaterals to see if we can make the circle hit every single vertice of these quadrilaterals. That's right, this unit and this lesson, we were supposed to use our compasses that are brand new. They're sitting in that classroom, just all alone. So sad. So we're going to take a look at whether or not we can make circles around these three shapes. The first one is a square, and of course we've already seen that. If you have a regular quadrilateral, you could definitely draw a circle that goes through all 4 points. Shape B over here, this one also can be drawn with a circle going through all 4 quadrilaterals. So now it's seeming like it works for all of these shapes. However, when we get to part C, there's actually no way to draw a circle around that quadrilateral that goes through all 4 points. It can go through 3 at the most, and that's a property about circles. A circle can always be drawn through any 3 points, any 3 non-collinear points. You can draw a circle that goes through those points. But 4, that's where things get special. In this case, we see 2 examples where it does work and 1 example where it doesn't. So what we're doing in this activity is, since we're drawing circles around shapes, this is what we call a circumscribed circle. Circum, like circumference, means to go around. Scribed, meaning to write. We are writing around the shape. It is circumscribed around the shape. We've seen a very similar word to this one before with inscribed. So we say that the quadrilaterals are inscribed in the circles, and we say that the circles are circumscribed around the quadrilaterals. Small difference there. So all of these, we're trying to circumscribe the polygon. Now, if this does manage to work, we call that a cyclic quadrilateral. It's a special type of quadrilateral because, as we can see, they don't always work. So A and B up top here would be perfect examples of cyclic quadrilaterals, and the one down here is not. 4.2, inscribed angles and circumscribed circles. We're going to be taking a look at the angles inside the quadrilateral, inside cyclic quadrilaterals, to see what makes it actually work and what makes it not work. So here we have a quadrilateral. We're told it is a cyclic quadrilateral, as we can see the circle circumscribing the polygon. We're given the measure of angle QRS is 105. We're asked to do a couple things. First, highlight the arc SQ so that it goes through P. That would be that arc right there. We know the measure of that arc because of the inscribed angle theorem. Angle QRS is the inscribed angle that is associated with that arc. So according to the inscribed angle theorem, that arc must be twice as big as that angle, meaning that it's 210 degrees. Now, if we highlight arc SQ that goes through R, it looks like this one. And now we can see that the entire circle has been highlighted. So the entire circle, the measure all the way around, would have to be 360 degrees. If we already have 210 degrees in the red, that must mean that the pink there must measure 150, because 150 and 210 make 360. And now that I can see that that arc measures 150 degrees, I can now figure out the measure of angle QPS, because angle QPS is an inscribed angle that's associated with arc SRQ. So if I take half the measure of the arc, I figure out that the angle measure is 75 degrees. So we start to see something happening here. When you have a quadrilateral that is inscribed inside the circle, all of the angles are inscribed angles. So we can use the measures of the arcs to help us find what the measures of the angles need to be. More importantly, we can see that the opposite angles have associated arcs that take up the entire circle. So what we're seeing here should be able to be applied generally. So let's see what I mean. Here we have a circle with angles just measured alpha and beta. But because we can look at these as inscribed angles, we know that the measure of arc DEF must be twice as big as the inscribed angle alpha. So measure of arc DEF is 2 times alpha. Take a look at measure of arc DCF. We figure out that that is 2 times beta, 2 times the inscribed angle. Once again, these arcs are taking up the entire circle. So when we put them together, they have to add up to 360 degrees. Divide the equation on both sides by 2, and we realize that alpha and beta have to add up to 180 degrees, no matter what alpha and beta are. So this is the main idea of this lesson, and that in a cyclic quadrilateral, the opposite angles have to be supplementary. So that's all the time we have for today, folks. Until next time, stay safe out there.